Every time a nuclear power plant falls behind schedule, the same question returns. Why does this keep happening? And almost every time, the answers sound familiar. It's regulation, it's politics, it's financing, or simply, China builds faster. For a long time, those explanations sounded convincing to me too. But instead of asking what people believed, I wanted to see what the projects themselves could tell us. So I started following the evidence. Construction records, reactor databases, technical reports, project histories. Not to prove anyone right, not to prove anyone wrong. Just to answer one simple question. What does the evidence actually say? I expected the data to confirm what I'd heard for years. Instead, the deeper I went, the more complicated the picture became. Project after project, country after country, reactor after reactor, one pattern kept repeating. And slowly, one uncomfortable thought began to emerge. Maybe we've been measuring the wrong thing all along, because in engineering, simple answers are rarely enough. And if that's true, then perhaps it's time to look at nuclear construction from a completely different perspective. At first, the story seems straightforward. Several recent reactor projects in China reached grid connection in roughly 6 to 7 years. Meanwhile, projects like Flamanville 3 in France and Vogtle Units 3 and 4 in the United States required significantly more time. Those construction records are real. They're part of the public record, and they deserve to be taken seriously. If we stop there, one conclusion seems almost unavoidable. Some countries simply build nuclear power plants faster than others. For years, that was the explanation I accepted, because the numbers appeared to speak for themselves. But engineering has a habit of challenging first impressions. Numbers rarely tell the whole story, unless we understand how they were created. Were these reactors based on the same design? Were they built under the same regulatory environment? Were they the first reactor of a new technology, or one of several built after years of experience? Those questions aren't details. They determine whether two projects can be compared in the first place. One observation appeared again and again during my research. The first reactor built with a new design often faces challenges that later projects may not. New manufacturing methods, unexpected engineering problems, supply chains still learning, construction teams gaining experience for the first time. Those lessons don't end when the reactor enters service. They become part of the next project. That was the moment when the timeline stopped looking like a simple race, because I wasn't just looking at construction speed anymore. I was looking at projects that had started under very different conditions, and that raised a new question. If these projects aren't directly comparable, what exactly are we comparing? After looking at enough projects, one thing became impossible to ignore. The numbers were real, but they weren't telling a simple story. Even within the same country, construction times could vary dramatically. Some reactors were completed relatively quickly. Others took much longer. The same was true across different reactor designs. Some projects followed a familiar engineering path. Others were stepping into completely new territory. That's when I realized I wasn't looking at one type of project. I was looking at several different generations of experience. Some reactors were the first commercial application of a new design. Others were built after engineers, manufacturers, and construction teams had already learned from earlier projects. Those two situations may look similar from a distance, But from an engineering perspective, they are fundamentally different. One pattern appeared repeatedly throughout the technical literature. The first project often carries the greatest uncertainty, not because the technology is necessarily flawed, but because the entire industrial system is learning at the same time. Design teams, manufacturers, quality control, construction methods, even the supply chain. Every unexpected challenge becomes part of the experience that future projects no longer have to discover for themselves. Suddenly, the timeline began to look different. Not shorter, not longer, just more understandable. The question was no longer, why did this reactor take 12 years? The better question became, what kind of project was it? And once I started asking that, another pattern slowly began to emerge. Not inside a reactor, but across an entire industry. By now, the investigation had taken an unexpected turn. I was no longer comparing reactors. I was comparing the industries that built them. Because every reactor project depends on something much larger than concrete and steel. It depends on people, engineering teams, manufacturers, specialized suppliers, construction experience, and those capabilities take years to develop. As I continued comparing projects, another pattern began to appear. In some countries, new reactor projects followed one another with relatively short interruptions. In others, many years passed before construction began again. That observation alone doesn't explain why one project performs differently from another, but it changes the questions worth asking. One recommendation appeared repeatedly in the OECD report. Maintain industrial capability, sustain supply chains, preserve construction experience. Not because continuous construction guarantees success, but because rebuilding lost capabilities creates additional challenges for future projects. That distinction matters, because preserving industrial capability is not the same as guaranteeing shorter construction times. It simply means that future projects may begin with knowledge, experience, and industrial capacity that already exist, instead of having to recreate them. At that point, I realized the investigation had changed once again. The question was no longer, which country builds reactors faster? It had become something much more fundamental. What happens to an industry when it stops building? By now, the original question felt incomplete. Not because it was wrong, but because it was too simple. I had started this investigation asking why some countries appeared to build reactors faster than others. But after comparing construction records, technical reports, and project histories, it became clear that construction time is only the final outcome. It doesn't explain how that outcome was achieved. Behind every construction schedule are years of engineering decisions, design maturity, manufacturing capability, skilled workers, supply chains, project management, and experience carried from one project to the next. Those factors don't exist in isolation. They interact, sometimes reinforcing one another, sometimes creating entirely new challenges. The evidence doesn't point to a single explanation. It points to a system where technology, industry, regulation, finance, and experience all influence the final result. And that changes the way we should read the numbers. Because two projects may finish in the same number of years for completely different reasons. And two projects separated by several years may have faced completely different starting conditions. Perhaps the real value of comparing projects isn't deciding which country is the fastest. It's understanding which conditions make future projects more predictable, more repeatable, and ultimately, more reliable. Because if that's the case, then construction time is only one piece of a much larger story. When this investigation began, I thought I was trying to answer a simple question. Why do some countries build nuclear power plants faster than others? After comparing construction records, technical reports, and project histories, I realized something unexpected. The evidence never pointed to a single explanation. Not reactor design alone, not regulation alone, not financing alone, not politics alone. Each of those factors matters, but none of them by itself explains the whole picture. Instead, the evidence suggests that nuclear construction is better understood as a system where technology, industrial capability, experience, supply chains, project management, and national policy interact with one another. Remove one element, and the outcome may change. Strengthen another, and the outcome may change again. That doesn't make the answer simple. It makes the question better. Perhaps, instead of asking, which country builds reactors the fastest, we should first ask, under what conditions can complex reactor projects be delivered more predictably? Because before we compare results, we need to understand the conditions that produce them. And that's where this investigation leads next. Not to a conclusion, but to another test. In the next part, we'll examine whether this idea holds up when we compare real countries, real projects, and decades of construction history. Because good questions deserve to be tested, not assumed. This is Reactor Atlas, exploring nuclear energy through physics, not fear.